All right. So the presentation is MPLS for ISPs with PPPoE over VPLS. My name is Thomas Krnak. I'm from Slovakia. I work for a company named Atris. The company has been around since 1991. We do complete IT solutions, servers, networking, virtualization, IP security systems, etc. I personally do network design, security, wireless servers, a lot of virtualization. MikroTik certified trainer as well. The agenda is basically PPPoE, basics and advantages it provides into the network, MPLS, VPLS, then some discussion about MTU and some MTU calculations, actual configuration, and then some ticks, trips, and problems. So the network we are going to be basing around this looks like this. It's as a provider, this is a fairly small network, obviously, for the show purposes, but what's important is that in this network, if you look at it, all the routers have full redundancy. So if something breaks in the network, there is always a separate route here. So yeah, like all of these links here, they can either be wireless or Ethernet or even wireless, doesn't really matter, but what we are going to do is assume that all of this is Ethernet and this is just backup wireless links. And yeah, this is basically the provider's infrastructure. So if we look at the client side of this, there may be, I don't know, 20 clients down here. There may be 10 wireless clients down here. There, you know, it doesn't matter if you are doing wireless or Ethernet or anything else, as long as it's, you know, Ethernet. So a few assumptions. For this presentation, I'm assuming that the network is fully routed. OSPF is already deployed and properly configured. Router IDs and loopbacks are properly implemented, so, you know. And PPPoE is an acceptable delivery method for your data services. And also, we are assuming that all devices support MPLS and jumbo frames. So the goals here, first of all, public IP assignment really shouldn't need subnets to stretch around the network. It's, we want to assign public IPs to our customers, and I mean these days with the IPv4 depletion, it's not been easy, at least for us. And one of the biggest problems is that if you have to move subnets around and assign subnets to the edges of your network because you want to deploy those public IPs, that can become a problem. So we want to conserve our public IP space with the use of /32s. So, I mean, in this network, like, what are your options, right? To serve a client a public IP, you have to stretch a subnet to him somehow. So you either have lots of small subnets around here, like this is all subnets, or you do something crazy and you bridge it into a VLAN and stretch one big subnet over here. I mean, you have to do it somehow, right? So we want to, you know, just get rid of all that trouble and just, you know, deal with /32s, and there you go, subnetting out of the window. So much easier. Then we want a single point for authentication and accounting, because that just makes it so much easier again. We want to secure and minimize the L2 segments. And we also, by implementing this, we can provide new services to our customers as layer 2 and layer 3 VPNs. So what we are going to use to accomplish all of this is PPPoE, point-to-point protocol over Ethernet. And basically PPPoE builds a point-to-point tunnel between two network devices. Direct layer 2 communication between the access concentrator and the client is needed for PPPoE to work. And, but since the tunnel is actually point-to-point tunnel, each client can and really should be its own L2 segment. Because that's the only thing you need. It's a point-to-point tunnel. You have to have layer 2 between the access concentrator and the client, but you really don't want the layer 2 segment to be any bigger than that, and it doesn't have to be. And of course, one big advantage with PPPoE is it supports full username and password authentication, even with radius. Because again, what are your options? You either do the HCP or static addresses, and you have to lock it down by MAC address, which is messy because there is ways around it, obviously, etc., etc. So having username and password, and then not having to worry about MAC addresses or anything like that, it just makes it much easier. So how we are going to accomplish this in this example network is that we will implement a tunnel terminator router and then 2 access concentrators for PPPoE. I have a star right there near the tunnel terminator. Ideally, and not just ideally, but you should have everything redundant. So you should have 2 of these tunnel terminators, and I mean, that's really easy. You just implement OSPF to handle the failover and redundancy, or you do it with VRRP. There are many options. Just for the simplicity in this, there is just 1 tunnel terminator. So what we will then do to enable PPPoE to work, we will build tunnels over our layer 3 infrastructure to tunnel the layer 2 traffic. And we will terminate the tunnels at the tunnels terminator and at the edge routers, which lead to our customers. And therefore, we will bridge the layer 2 segments all the way from our customers through our network, all the way to our PPPoE access concentrators. I mean, in this example, there is just a few routers, but it can easily be 100 routers between the customer and our access concentrators there, and it wouldn't matter. Like I said before, our goal, or not goal, we just need it for PPPoE is we really need to stretch that layer 2 segment or layer 2 traffic over our existing layer 3 infrastructure. So EOIP could be a solution for tunneling layer 2 over layer 3. I mean, it's basically, it works, right? The problem with EOIP really is to avoid fragmentation. In EOIP, you have to do some crazy things. Like since EOIP works like it works, and a layer 2 frame is always going to be much bigger than what you can fit into a layer 3 packet, I mean, fragmentation becomes an issue with EOIP. And also there are performance issues compared to MPLS. So with VPLS, we get no fragmentation at all. We can transfer full 1500 byte packets, and it's actually, you get 60% more performance over VPLS than you get over EOIP. And I mean, that's an old slide, because since then, FastPath has been implemented and MPLS support FastPath, so these days it's even more. But you can, at worst case scenario, if you turn off FastPath, you still get 60% more performance out of VPLS. So what's this VPLS I've been talking about? VPLS is virtual private LAN service, and VPLS is basically a method or a standard to create transparent layer 2 tunnels based on MPLS signaling. So a VPLS tunnel is presented to the router as a separate interface, just like EOIP. It's for the router, it's an interface like any other interface. And VPLS tunnels add 1 VPLS tag into the MPLS frame. So what's an MPLS frame then? So MPLS is a protocol, it's a multi-protocol label switching. And in MPLS networking, or in MPLS switching, each data frame is assigned a label. Then packet forwarding, or in case of MPLS it's switching, switching decisions can be made solely on the contents of this label. There needs to be, you don't need to examine the packet any more than read a 4-byte label, and you know exactly what to do with the packet. There is no reading of source, destination, IP addresses, etc. It just doesn't need to happen. And that's where the speed comes from. So you get the speed benefit since no looking at the contents of the packet, you don't have to look into the IP routing table, and it just is so much faster. So MPLS and label switching. MPLS is considered to be a layer 2.5 protocol, just because it falls right in between layer 2 and layer 3. And then there are the MPLS tags, which we already mentioned. And the MPLS tags are added between layer 2 and layer 3 headers. So we have a packet down here that is an MPLS packet, or rather an MPLS frame. And you can see a VPLS tag is just one of multiple possible MPLS tag types. You have basic MPLS tags, then you have MPLS QoS tags, etc., etc. The point is that there can be many different frames in there which MPLS supports. MPLS is really yeah, you can have as many frames really there as you need. So, there will be a major discussion about MTU because MTU is a problem with MPLS usually. So MTU is maximum transmission unit, and MTU basically defines the maximum byte size of a frame that the device can handle. So frames larger than maximum allowed MTU are silently discarded, and this is very important. No ICMP or any other kinds of errors are produced when a frame is dropped because of a MTU issue. There is no notice. The frame is just dropped, it's dead. You get nothing. And it's very important to realize this and be aware of this. So why is MTU even an issue and why are we talking about it? Where for a normal switch or a router, a normal frame would look like this. We don't have to care about the inter-packet delay that is automatically taken care of by the interface drivers, and also we don't have to take care of the checksum at all either. Those are completely transparent to us and we just don't care about them. It's same with all devices that I've seen, switches, routers, MikroTik, it doesn't matter. All this is automatically taken care of by the device driver. So a normal frame for a switch or a router would be 1500 layer 3 MTU and 1514 layer 2 MTU. But what starts to happen when you start adding all these tags, MPLS tag 1, 2, 3, 10, 20, the MTU rises. And the layer 3 MTU stays the same, but the layer 2 MTU can go up a lot. So in this simple example, just by adding a VLAN and 2 MPLS tags, let's say one is a MPLS main tag and the other one is an MPLS QoS tag, we already have a layer 2 MTU of 1526, which is more than the usual 1514 by quite a bit. Right, so cheap and unmanaged switches usually only support L2 MTU of 1514. And I mean, when you have good switches, they either support jumbo frames, bigger MTU frames, or you have to enable the jumbo frame support to get frames over 1514 MTU to pass over that switch. So you have to make sure that your layer 2 infrastructure will not drop your MPLS frames. And this is the biggest and most common problem with implementing MPLS that I've seen. So a small update for MikroTik. For MikroTik, this is a page right out of the wiki. You can look it up. For MikroTik, this is what different types of MTU MikroTik recognizes and how they are calculated. If you notice, MikroTik doesn't include the Ethernet header into the L2 MTU calculation. And this is another thing. Check your switches, check your other routers if you have anything than MikroTik, and make sure how the MTUs are calculated. Because usually for switches, their L2 MTU value actually is with the Ethernet header already calculated in. With MikroTik, it's without. So this is another consideration, just make sure you know exactly how it works, just to avoid further problems and confusion. So let's go over an actual MPLS frame. This is already a frame of PPPoE inside a VPLS tunnel carried by MPLS inside of a VLAN. Our goal here is for our clients to not even know that something is happening with their frames that we are encapsulating, etc. So what we want is we want to deliver full 1500 layer 3 MTU capability for our clients, so there is no need to change MSS or anything else. And this is how a frame would look like if we wanted that. So if you look at the whole frame, all the way up here, what the Ethernet interfaces on our network infrastructure, on our switches and routers, etc. receive is actually 1548. And I mean, at this point, we are about 20% over normal frame size. So, this frame would just be dropped without any notice if you have just a simple, single unmanaged switch inside of your MPLS path, it wouldn't work. So you can see this whole calculation, and this is based on MikroTik. So the full frame Ethernet interface MTU will be 1548. Then the actual Ethernet interface layer 2 MTU for MikroTik, which is different, would be 1534. Then you have the VLAN interface, which has its own MTU because it's an interface on the router. Then you have the MPLS MTU, which is also a separate thing you need to configure and make sure. Then you have the VPLS interface, because again, that's an interface, so it has an MTU value. And then there's full frame and L2. And then you have finally the layer 3 MTU. If you notice, the layer 3 MTU is only calculated, and we only care about the layer 3 MTU on the last interface. So all the way down through this, the only L3 MTU we care is on the VPLS interface, and then we just care about the MPLS and L2 MTUs. So let's see how a packet like this actually looks like in Wireshark. And oh, the resolution is so small. So this would be a packet that we were talking about in Wireshark. You can see it's 1548 bytes, and you can see it all the way down. If we start, this was just a simple ping. So this is basically layer 4 header and then data. So data for us is 1472 because then we have 8 bytes of ICMP header. Like we weren't talking about layer 4. So for us, this is all data. This is 1480 bytes of data for us. Then we have the layer 3 header, the IP header. Then we have the PPPoE headers. Then there's the Ethernet frame, which we are encapsulating inside of the VPLS tunnel. Then you can see the VPLS ID. You can see the MPLS label that was attached. Then it's inside of a VLAN. And then you can see the actual Ethernet frame that encapsulates all of this. So this is basically this exact frame we had here in Wireshark. So let's talk about MPLS now that we are through MTU. So how does MPLS really work? So MPLS basics. If we look at the router, each router assigns a separate label to each prefix in the routing table. Then each router tells its peers about its label bindings. So if we take a look from the point of view of the MPLS cloud, each router in the MPLS cloud assigns its own label to every prefix in the routing table, and then every MPLS router tells its peers about its label bindings. So this way, all peers know about each other's labels bindings. But we have to think about this only on the peer level. So if a router is 2 hops down from me, I don't know its label bindings anymore, and I don't care. So it's just the peers. Each router or each peer knows its other peer's label bindings. So how does this actually look in software? You can easily see this in the MPLS window. You go to local bindings, and then remote bindings. So you can easily see what my bindings are and then what all of my peers' bindings are. So what is then done with all these bindings is that the router can build an MPLS forwarding table. The router, and this is all done completely automatically. You don't have to care about this. It's just you need to know how it works, but you don't have to assign labels, etc. Like I said before, the router, since it can talk to its peers, they can make sure that every single prefix has a unique label for me and all of my peers. This is all done automatically. But after all this calculation is done, the result is an MPLS forwarding table, and you can see that if this router receives a packet with label 55, it will attach it a label 165 and send it to a certain peer. So that's how MPLS forwarding goes. You just build a forwarding database like with any other forwarding database. It's just based on a different principle. So how are all those labels processed? There is a protocol which is called LDP, Label Distribution Protocol, and LDP allows the routers to learn the label bindings of their peers. It's a rather simple protocol. It just runs over IP, UDP and TCP on port 646. So let's look at the router roles in an MPLS network. And there are basically two roles that the router can have. It will either be an LER, so a label edge router, or an LSR, a label switch router. The important note about this is all considered per an MPLS path. So a single router can actually be an edge router and a switch router at the same time. It just depends on how you look at this. So for example, for this example, that's really easy. But just if we draw another subnet right down here, this router will be an LSR for this path, but for this path, this router will now be an LER. So actions that can be performed on an MPLS frame. There are 3 actions that the MPLS router can perform on a frame or an MPLS switch. That's push, so add an MPLS label, pop, remove an MPLS label, and swap, so change the label. And if you look at this, the first 2 actions can only be performed by the LERs, so only the LERs need to push and pop labels. All the LSRs only need to swap labels. So here is a look at a full MPLS forwarding table. Like I said before, you can see all the labels in here. You can see when I receive a label frame, what label will I swap on there. If there is no out label, then I will pop the label, etc. And this is from actual other network. So this is live MPLS cloud. So PHP. We are not going to do any programming. This is MPLS PHP. Stands for penultimate hop popping, and PHP in MPLS is implemented for performance reasons. So let's look at this. Without PHP in MPLS, the LER would have to do 2 lookups for a frame. Since a frame coming is an MPLS frame, I need to do an MPLS forwarding table lookup to find out what I need to do with that frame. But then I find out, okay, so the destination for the frame is not MPLS enabled, which means I cannot send that frame as an MPLS frame. So I need to send it as an IP packet. So what I need to do is that now, after doing a lookup in the MPLS forwarding table already, I need to go and look into my IP forwarding table and look in there as well. And this might not seem like much of an issue, but it is. It really gives the edge router a lot of work. And this PHP just solves it. So what actually PHP is, if you look at this simple scenario, an MPLS untagged frame comes in from here. The LER will push a label, and then the frame will get forwarded, right, throughout the path to its destination. So like we were saying before, if PHP didn't exist, this frame would still be an MPLS frame. This router would get it. It would have to look in the MPLS table and figure out it needs to deliver it here to the destination, which isn't MPLS enabled, so it would have to do another lookup. So what PHP actually does is that the MPLS tag is popped on the router before the destination. So by its name, penultimate hop popping, so before the ultimate router, the tag is popped. So what will happen is the pop will happen here, and this frame will not be an MPLS frame anymore, it will just be an IP frame. And this router doesn't have to do 2 lookups. It knows where it needs to send the frame, it just doesn't send it as an MPLS frame anymore. So this router only does an IP table lookup, and it's just a normal routed frame after that. So there are some complications, and some major complications in MPLS with ICMP. So in an MPLS network, an ICMP error packet is forwarded all the way to the destination, not to the packet's source. So the source of a packet, for example, TTL runs out, so the ICMP error needs to be delivered back to the source of the packet that caused the error. This is what normally happens in an IP network. In an MPLS network, the ICMP error is actually switched all the way to the original packet's destination and then switched back to the source that caused the error. So how it would look like is if I was transmitting a frame which timed out because of TTL on this router, normally this router would return an ICMP error back right away. In MPLS, when a frame or a packet times out because of because of TTL, an ICMP error packet will be created, but it will be switched all the way to the last router, which will pop the label. It will run it through the routing engine. Inside of the IP routing engine, it will find out that it's an error packet, and you know it shouldn't go to the original destination. It should go back. So it will go back all this way. This is the ICMP behavior in an MPLS cloud. So you might be wondering, why is this even an issue, and why would MPLS do this? Well, this behavior is implemented because an MPLS switch doesn't even have to be a router. It's MPLS. It doesn't have to have an IP layer at all. Like, labels can be distributed other ways than just LDP, which runs on an IP. Also, the MPLS switch, it might not even have a route to the source of the original packet that caused an ICMP error. This will happen in layer 3 VPNs. And I mean, the MPLS switch, as I said before, it might not even support the IP protocol. It might not even understand ICMP. All the MPLS switch cares about is that it can read labels and make switching decisions based on the labels. So this is why ICMP behaves as it does in MPLS. So the implications of this. In MPLS networks, when using trace routes, remember how it behaves on the back end. So as long as there is a break anywhere on the MPLS path, the packet will not make it past first hop. But that does not mean that the second hop is dead. Since the ICMP error has to be forwarded all the way, a packet might not be transferred by the 6th router in the MPLS chain, but you will not get an ICMP error back. So implications 2, ping times will not be reported correctly. Well, not correctly like we are used to them. Because of this behavior, because the ICMP packets have to be forwarded all the way, the only ping time you will see for all the hops is a full round trip. So if you look at this example, this is an MPLS trace route with pings. You will see that right at the first hop, I get 13 milliseconds. And those 13 milliseconds are the same for all the hops. That's, again, because of how ICMP behaves in MPLS. Normally, the graph would look like this, right? The latency gradually increasing over hops, not in MPLS. So, MPLS packet behavior, there is another very important thing to note. MPLS, it's switched traffic, which means MPLS traffic doesn't pass through firewall, doesn't pass through NAT, doesn't pass through Mangoes, to QoS, etc., etc., etc. This is very important as well. Only on the label edge routers, on the LERs, the traffic will pass the routing engine, but not on the LSRs. So why is this? By the way, this might look extremely complicated, but once you learn it, it is very useful. So what actually happens is, this is how RouterOS processes packets. And you can see that if it's a layer 2 packet and it needs to get switched, it just goes this way. If it's an MPLS packet, it goes this way. If it's an IP packet, it goes all the way this way. The point is that the firewall and QoS and everything is in this box. MPLS frames don't go through that box. But, as was said before, they do on the edge routers. Because on the edge routers, either the packet that comes in doesn't have a label yet, so it's not necessarily MPLS frame, so it will go all the way through this. And on the outbound LERs, the packet doesn't have a frame anymore because it needs to be passed to the routing engine. So then again, and yeah. So how do I MPLS? This is the configuration part. So configuring MPLS is actually not difficult. Configuring MPLS is really simple. It's just you have to be aware of all the concepts and how it works. So all you need to do for MPLS, first of all, here we go, MTU. you have to change the maximum allowed MPLS MTU for the router. So you just have one line, you go into MPLS interface and you set max MTLS MTU, there you go. You enable LDP to get the router to change labels with its peers. And here is a very important thing. For MPLS to work correctly, like I was saying before, we are assuming that your network is properly configured for OSPF. I don't mean OSPF turned on. I mean OSPF done properly. So in this case, we turn on LDP, enable it, give it our router ID, which should be a reachable IP address on a loopback interface, as a LSR ID and as a transport address. And then we just add an interface on which we want the LDP process to run. So yeah, like I said, remember that the router ID should be from OSPF, should be reachable, should be on a loopback, etc. So adding VPLS to the tunnel terminator. The VPLS is an interface like any other, and it's a tunneling interface. So we just, and again, here we go, MTU. We have to remember that we want to pass full 1500 byte packets, but there is that PPPoE header we have to count in. So L2 MTU for the VPLS interface will be 1508. We'll give it a name and we'll give it a remote peer and then tunnel ID. It's just like EOIP. So in this example, we would build two VPLS tunnels to our peers. Then we would create a bridge. Again, L2 MTU, watch out. And then we would add some ports to the bridge. So like the two VPLS tunnels and then an interface which would be facing towards our PPPoE access concentrators. So now you will notice one thing in here, horizon equals 1. So what is this and why is it there? So on router OS, what we do to secure the layer 2 segment, because like I was saying before, the layer 2 segment at this point should really be one layer 2 segment per one customer. And so how do we do that is the bridge split horizon functionality, which will allow us to secure the layer 2 segment. So how it works is that only ports with different horizon value can communicate with each other on layer 2. So by configuring these ports in the bridge with the same horizon value for all three ports, we've eliminated layer 2 communication between these ports, which is what we want. So let's look for an example of a wireless IP that would connect my clients. Again, MPLS is not that hard to configure. Just give it the MPLS MTU, enable LDP, turn on the interface that I want the LDP process to run on, and create a VPLS tunnel back to the tunnel terminator. So let's look at a fast configuration of how a example PPPoE access concentrator would look like. We just create a PPP profile. In ideal case, we would provision everything from radius. So we enable radius, create a radius peer to configure, and then just turn on the PPPoE server. The important thing, again, is to mine the MTU, because our goal was to provide a full transparent 1500 MTU over PPPoE. So we have our infrastructure secure, our layer 2 traffic is fine, but what about the other part, the part of our infrastructure that's facing our customers? And this will be your wireless IP or a switch which you plug all your customers into, or something, right? Fiber or something. It doesn't matter, but we still need to secure it. So PPPoE, as we said, being a point-to-point tunnel, it only requires layer 2 connectivity between the endpoints, nothing else. So for security reasons, it is desirable to block direct layer 2 communication between the customers, so they are protected, so you are protected, and nothing bad happens to anybody. So because if you look at this, the only thing we are providing to our customers is PPPoE. So there is nothing stopping anybody to just throw up a DHCP server on our layer 2 segment and then assign DHCP IPs to our customers, and then he knows all the IPs. I mean, ideally that wouldn't happen because the router on the customers, the CPE, would be switched into the PPPoE client mode, but who knows what's on my network, right? I don't have control of my customers. So we really want to protect them and ourselves and our infrastructure. So for wireless links, this is really simple. You just uncheck the default forward. And for wired clients on your access switches, enabled port isolation. So that's how it looks like. It's really simple. Just uncheck the default forward box, or if you have switches, simply use the port isolation. I guess you guys can't really see it well on the projector, but yeah, basically you isolate all the ports on the switch from talking to each other, and there you go. Again, you are accomplishing, having a single layer 2 segment for every single customer right here. So accomplishing the goals. Right now, after all of this, what our infrastructure would do is that we have the tunnel terminator, which bridges the tunnels and the interfaces on these routers all the way down here to the access concentrator. And every single client that will connect, if he connects to this switch, he cannot communicate over layer 2 or layer 3 or anything with anybody else on that switch, which is what we want. And at the same time, if he configures a PPPoE client on his device, it will get an IP address from us and it will work properly as it should, without any MTU issues, etc., without the need to change MSS, etc., etc. So, tips. L2 VPNs. Just by implementing this, and we implemented this for different reasons, but since we already implemented this, we get to have a new product. You can now offer a service for your customers of transparent L2 VPNs just by building a VPLS tunnel and bridging it to their interface. There you go. There's a new business product that you can offer them for you right there as a side product of what we did. And again, you can sell this really easily, because for you as a provider, all you need to do is configure a single VPLS tunnel. You don't have to even mess with QoS or anything else, because it's already in place for that customer, and you are providing it with a transparent, transparent VPN. And he doesn't have to do anything. He just plugs his device into a port, and it's layer 2 bridged all the way to the other side, to the destination. So you have a new service for your customers without actually implementing anything, because we've already implemented this because of PPPoE, right? So another tip, if something is not working and you are sure your configuration is correct, it's MTU. Again, because of the behavior of MTU and the silent discarding of packets, it's most of the times that I've seen, it's just MTU, MTU, MTU. So look for unmanaged switches across the MPLS path. Make sure jumbo frames are supported and enabled throughout all the equipment on the MPLS path. So another thing to do is watch out for cheap network cards. Some network cards will not report their max supported L2 MTU to router OS. What actually happens in software is, at this point, a router OS doesn't know the network card's maximum L2 MTU, and it ignores any frames that are bigger than 1500 on layer 3 or 1514 on layer 2. Even if the NIC actually supports jumbo frames, if it doesn't report that max L2 MTU value to router OS, it doesn't work. This is, of course, only a problem on an x86, or if router OS is a virtual machine. On all router boards, this just works. So, as I was mentioning virtual machines, there's an ESXi tip for you. If you are using virtualized router OS, again, MTU, you have to check that the vSwitch that's assigned to the virtual machine's port actually supports 9000 or, a jumbo frame. An example right here would be that, so, you would enable 1600 MTU frames on that virtual machine's port, and you would think everything is just fine and it's going to work. Well, E1000 network card in ESXi doesn't support MTU over 1500, even if the vSwitch does. This is actually because E1000 virtual NIC doesn't report its max L2 MTU like we were discussing before to router OS. So what you actually have to do is you have to use E1000E. And that's another funny thing, because if you are virtualizing MikroTik router OS, you're going to select the OS type as Linux, 32-bit, And in ESXi, you cannot assign E1000E virtual interface to that machine, so you actually have to manually edit the VMX files. It works after you edit the VSX files, but I mean, this took me a week to fix. Because you would expect, right, you configure the vSwitch and it works. Well, nah, not that simple. So MPLS binding issues. Currently, RouterOS creates a label binding for all prefixes in the routing table, like we were discussing before. The problem is that label bindings are created even for next hops that are not MPLS enabled. And this is an issue because if you set an MPLS frame to an MPLS not enabled device, it's just going to be an invalid frame and be dropped. So watch out for this on the LREs, on the edge routers, and manually create explicit null bindings as needed. There is a special note here. There was a bug in versions less than 6.3 where you could only create one explicit null binding per a forwarding table. It's been fixed since. Just be aware that there's a bug and just upgrade to the newest version and it will work. So MTU issues, they just keep popping up, man. They are everywhere. So even on RouterOS, there are MTU issues. Currently, a bonding interface does not report max L2 MTU. So if you use MTU higher than 1500 on a bonding interface, it will not work. So if you do any kind of bonding on RouterOS, it will not work, no MPLS. The bug is reported, hopefully will be fixed. So issues, L3 VPNs. Sadly, L3 VPNs are currently broken in V6. There is a lot of problems that I'm not going to go into. Use V5 if you need L3 VPNs and test, because even in V5 there is a couple of issues. And yeah, currently L3 VPNs due to this are not possible in the CCR. Basically, yeah, there's been emails to support and let's hope for version 7. So problems with PPPoE, that's another potential problem. One problem is a delivery mechanism like this, PPPoE, since it's point-to-point tunneling, is IPTV. If you want to deploy full triple play in your networks, I mean, you have to implement IPTV with multicast, and multicast requires a routed network for it to work. But you are providing your data over a point-to-point tunnel for each customer. So therefore, multicast will just do nothing. So consider deploying multicast besides PPPoE, for example, in a separate VLAN, and I mean as a VLAN to the customer, not as one VLAN through your whole network. That would be a bad idea. But the overall state of MPLS and MikroTik, it's functional, it's deployable and deployed in production. It works, minus the L3 VPNs. And as long as you are aware of how MPLS works and the ICMP works, etc., it's a great tool in MikroTiks and your own toolkit. So final notes. Yeah, this presentation is by no means a complete, ready to implement solution. MPLS and its deployment, you really have to look at your network. You have to decide what you want to do, and it requires considerations and planning. And as we said before, that was after we already assumed that OSPF and everything else is running and properly implemented. So more material, if you like this presentation, I have a couple of more presentations on TikTube you can take a look at. So yeah, if you have any questions, go ahead. Anybody?
If you were starting a small ISP from scratch, at what point would you begin implementing MPLS?
Right from the beginning. Right from the beginning, it's just so much easier. I'm not saying it cannot be done after. I mean, with MikroTik we have scripting, so if you do it properly, you can switch a whole network from being a routed or a bridge network to a fully routed MPLS network in 5 minutes with scripts. You just would have to do a lot of scripting in advance and then deploy it, right? But I would say from the beginning. It just saves you trouble down the road, and when you need to expand really fast, you have the option and everything is ready. DSL as in what?
VDSL or ADSL or
It's usually so. Yeah, I don't know if you guys heard the question, but if there are any problems with DSL, usually you would use DSL as a transparent transport, right? So it would be in what is it, MPLA bridge mode, right? So you have to like you have the DSLAM and the modem, but for you, yeah. Yeah, exactly. It's for you DSO or anything else. Yeah.
Provided with edge is MikroTik, terminating all the MPLS to one side. On the other side, because most these lanes, right?
Yeah, you don't care. You just don't care. For you, DSO is just a transparent transport technology. Yeah. There was, yeah.
You know, creating your labels for the MPLS, do you have a recommended numbering scheme that you guys?
The labels are completely automatic. There is nothing you need to do about labels. It's all taken care of by the MPLS process and the protocol itself. So it just works with the labels.
You were talking about MTU size being an issue.
Yeah.
So if you're using MikroTik products for the wireless side,
Yeah.
most of the products don't support.
No, the max LTU for wireless is 2290.
On the label, okay. So you're not talking about the physical interface MTU like that?
It's just layer 2 MTU. Yeah, it's the physical. Like usually in MPLS, because of PHP and all the stuff, you don't want your individual. Like if you have two SXTs making a point-to-point link, you don't want them to be routers. You just want them to be bridges, right? So they don't care about the traffic. They are not doing anything with the traffic. All they care about is they see a layer 2 frame that's like we were discussing 1564 in size. Their max MTU. You of course have to configure the interface to have enough MTU, right? Because if the MTU on the interface is lower, the frame will be discarded. But max allowed MTU on MikroTik wireless links is 2290. It works. As long as it's configured, of course. Yeah.
Your example here is talking about PPPoE. Do you use it with other flavors instead of if you didn't want to put PPPoE on your network?
What do you mean? Like?
Hotspot authorization.
Well, yeah, that's why we were discussing it. You know, like I was saying before, you have more options than this, right? You can bridge your network. Don't do it, but you can, right? You can do DHCP on the last mile. You can do static IPs. You can do hotspot. There's many options. It's just with like I was saying before. The point here is that it's all tunnels and /32s. So like by the time you get to this, like injecting the public IPs and routing and everything into OSPF is just a one checkbox. Redistribute connected routes, and there you go. And it just makes it much easier because you don't have to deal with those subnets and you don't have to deal with stuff like that, because even in hotspot, right? And again with hotspot, how easy it is to make, because you have to have layer 3 and layer 2, right, for hotspot and everything. So how easy it is for somebody to just spoof attack your main gateway's IP address, and your network is not going to work. Of course there are protective methods, but what I'm saying is that with this you just don't have to care. The only thing you have to do is enable port isolation, and there you go. It just solves many issues. I mean, as you said, there are many different ways to do your network. This is just one of the ways that you can do it. And as I said before, the biggest problem with this is IPTV. Yeah? Well, it's encapsulated inside of a tunnel. Again, the VPLS tunnel is a point-to-point tunnel. So if there is broadcast, the only way the broadcast is going to come out is on the end of the VPLS tunnel, which is also a customer site. Do I what? Yeah, we don't care. As a provider, what we provide is an Ethernet port that is a transparent bridge to another Ethernet port at another location. What the customer does with it is his thing. If he tells us to give him a router or something, we will do. Sure, no problem for us. We'll be happy to give you anything you ask for. But usually we just tell them, plug something into this port and it will come, at the other side. And as I said, it's a point-to-point tunnel. So like you said, broadcast control, you just don't have to care about it because it's point-to-point. Anybody else? All right. Well, thanks for coming. I know it was after lunch, so